In this video, I will explain convolution property from the Laplace transform, right? So, statement, standard statement and derivation of convolution property. So, first see convolution. This operation explains similarity between the two functions. So, this is the symbol of the convolution. One star symbol is used like this. So, we have to draw like this. This explains the convolution symbol, right? And convolution explains the similarity between the two functions. Similarity between two functions. So, those two functions I am writing like this now. X1 of t convolution with x2 of t. It should be like this, right? Then we have to find the Laplace transform of this. Laplace transform of x1 of t convolution with x2 of t. So, in time domain, convolution operation becomes multiplication in frequency domain. Multiplication in frequency domain means this side it becomes here x1 of s into x2 of s. So, here I have wrote convolution symbol, but here I am writing multiplication symbol. In one domain convolution, in another domain it becomes multiplication. This is the standard statement of convolution property. So, for the purpose here I am writing few statements. Laplace transform of x1 of t is x1 of s and Laplace transform of x2 of t is x2 of s. So, if it takes Laplace transform of the individual functions, those are x1 of s and x2 of s here. So, Laplace transform of x1 of t is x1 of s and Laplace transform of x2 of t is x2 of s. Those are individual Laplace transforms. And if you apply the Laplace transform of convolution of these two functions, then frequency domain it becomes multiplication of frequency domain function. So, x1 of s into x2 of s. This is standard statement of convolution property. Now, we have to prove this. So, to prove this purpose, again I want to take here one standard functional representation of convolution operation here. x1 of t and x2 of t. Convolution of these two functions becomes like this. The integration is from minus infinity to plus infinity, or one side we can write here 0 to infinity. The first function we have to write with other variable, here t variable is there. Now we have to write with tau variable, x1 of tau into x2 of t minus tau d tau, right? So, here I am writing with the tau representation. Tau explains the one scanned variable or dummy variable. So, write the complete function in terms of another variable. x1 of tau into x2 of t minus tau d tau. This is the standard equation of convolution operation, convolution of two functions. Now, we have to prove this statement here. So, we have to prove this property from the Laplace transform. For that purpose, first of all, I am taking here LHS. LHS explains the Laplace transform of x1 of t convolution with x2 of t. x1 of t convolution with x2 of t. Then the Laplace transform equation explains the integration from 0 to infinity, the given function, right, as it is here, x1 of t convolution with x2 of t into e to the power of minus st dt. Just here I have applied the basic Laplace transform equation, the given function into e to the power of minus st dt. Then replace this complete function x1 of t convolution with x2 of t with this equation here. Substitute this equation here, then it becomes the integration from 0 to infinity. If this part is replaced here, minus infinity to plus infinity, right? So, otherwise we can write here limits are 0 to infinity because if it takes unilateral, then it becomes 0 to infinity. x1 of tau into x2 of t minus tau d tau into e to the power of minus st dt, because the complete function defined with respect to t. But this convolution equation explains in terms of tau, right? So, here two times integration is there, one time integration with respect to tau and one more time with respect to t. So, two integrations. That is why here I want to write separate integration parts here. So, first of all I want to write integration with respect to t here, right? That purpose here I am writing x1 of t outside, x1 of tau, and the remaining function 0 to infinity x2 of t minus tau into e to the power of minus st into dt. So here this integration with respect to t is there. So all the t functions defined within this integration. And later I want to perform the integration with respect to tau. Now this is similar to one shifting property, right? So the shifting property explains Laplace transform of x of t minus t naught. Laplace transform of x of t minus t naught explains the e to the power of minus st naught into x of s. Shifting in time domain, exponential function multiplies in frequency domain. Then how to write the functional representation here? This equation explains integration from 0 to infinity. The given function is x of t minus t naught into e to the power of minus st dt. So already we have derived this equation in shifting property. So whenever the shifting applies in time domain, in frequency domain it multiplies the exponential function. So that is equivalent to like this. So integration from 0 to infinity x of t minus t naught into e to the power of minus st dt becomes e to the power of minus st naught into x of s. Now this equation, this is also similar to this function. So here x2 of t minus tau, how many times shifted here? Tau times into e to the power of minus st dt. Then this function is completely replaces with e to the power of minus s tau into x2 of s, right? So then this function becomes, this is one standard property, right? From this property that I am writing now, integration from 0 to infinity x1 of tau into, this is I am replacing with this equation e to the power of minus s tau into x2 of s with respect to tau. So this complete integration defined with respect to tau, and the remaining variables becomes here constants. So that's why I am writing x2 of s is outside, right, like this. And what is the remaining function now? x1 of tau into e to the power of minus s tau d tau. This is similar to the basic Laplace transform formula. So again I am replacing this complete function with the Laplace transform of x1 of tau, that is x1 of s. So finally becomes here RHS. LHS is equal to RHS, hence proved, right? So Laplace transform of convolution function becomes here multiplication in frequency domain. The convolution property statement explains in one domain convolution operation, another domain it becomes multiplication. So a time domain convolution, in frequency domain it becomes multiplication operation. So please take this now.